or a little bit less than a minute left.
Yep.
Okay. Okay. Maybe let's start now. Okay, I'm happy that Yen-Kheng is giving a talk today. So this is a talk in a short series. Next week, Mounir Nisse will give a talk on a related object, on a related topic. So it's all about A-discriminants. I don't know what it is, but apparently it is a hot topic right now. At least it's a hot topic in our department. So I don't think that I need to introduce Yen-Kheng, Professor Lim Yen-Kheng. Everybody knows him. He is here since, well, at our university, at our department since more than 3 years. Well, everybody knows him, and also the students, I guess most of them know him. He is giving regularly talks in our seminar, and he is a very productive colleague of our department. Today, he wants to talk about some curves around black holes, so-called light rings. More or less, as I understand this, these are some closed curves around black holes where the light is traveling in a closed curve. So, and he has apparently used here some new mathematical technique. So he gives a talk on light ring pairs from A-discriminantal varieties. And maybe I should mention right now the talk Mounir Nisse is giving next Tuesday. This is phase limit sets of A-discriminants and beyond. So if you're interested in, if you find this talk today interesting, maybe don't forget to visit, to join Mounir Nisse talk next time. Okay, so let us start. So Yen-Kheng, please start your talk.
Okay. Thanks, Peter. Thanks for the introduction. So I hope everyone can hear me. Let me know if you can't, but I will go into full screen mode. Okay. So thanks everyone for joining this session. I'm here to talk to you about an exciting result that Mounir and I have got recently. So what we did was we are using a theorem about A-discriminant to answer a question about light rings, which is a problem in gravity. So these two topics are usually not typically connected to each other, but in this sense, somehow we managed to find a useful theorem to address a question, which I will explain more in the following. Okay, so this is the work, as I said, which I did with Mounir, who is also here. And it has just been accepted by PRD, and it will come out probably, hopefully, by the end of this week. Mounir himself next week will also give a talk about A-discriminants. So, like Peter said, we can kind of view this like a kind of a two-part series of talks, or maybe a mini workshop. My talks consist of 4 parts. The first part will be non-technical, and hopefully it will be for students and those who are not familiar with relativity to understand, and to at least understand what kind of problem that we are trying to solve. And then after that, I'm going to derive the geodesic equations, and then go to discuss a little bit about A-discriminants and to see how these two are connected to each other. So in the final part, I will tie everything together and explain how we will use a certain theorem about A-discriminant to say something about the existence of light ring pairs around compact objects like stars or black holes. So yeah, so let's get started with the first part, which is non-technical. I guess I'll start with the picture, the very basic picture for everyone who has not heard of relativity before. So in essence, general relativity is a geometric theory of gravity, which is to say that the force of gravity is a manifestation of the curvature of space-time. And therefore, it will have the effect on the motion of light. So if we don't do anything, right, light will naturally travel in a straight line. But if it's passing through close to a source of gravity, then the path of light will be bent. For example, this phenomena has been observed by Arthur Eddington in 1922, where light from a star passing close to a sun will be bent. And this is how, and the observation was made on Earth. So this is for the sun. In space, right, there are objects that are way more massive and way more dense than our sun, like black holes or like white dwarfs, neutron stars, boson stars, all things. These have very high densities and the gravity will be very strong. So for those highly massive objects, we can expect that the path of light can be bent all the way until it makes a circular motion around the star. And this is what these are the light rings that is in my title and will be the main subject of my talk. So we are talking about light that is going on circular motion around a gravitating source. Okay, so a bit of motivation first. Why is light ring research important, especially nowadays? The main reason is because light ring can be directly and indirectly be observed using recent breakthroughs in technology. So one of the big news back in 2016 was we managed to detect managed to have a direct detection of gravitational waves. So gravitational waves, these are like it is a phenomena where two black holes are being attracted by each other's gravity and they spiral into each other and then they crash into each other. So this is an extremely violent phenomena and it will send ripples of space and time all across the universe. And some of them happen to pass by the Earth and now we can detect them in this signal that looks like this over here. So it is an extremely fascinating phenomena and you know, one can give like 2 hours lecture just about this, but for today, for light rings, the important point is this part here. So after it has merged, it has formed a larger black hole that right after being formed, it was a violent process. So it is still very energetic and the final black hole is still vibrating and pulsating. So it's still having a lot of energy and it will take some time to settle down. So this settling down is a decay of energy, and this decay is an exponential decay. And the decay constant, we do have a formula to derive this decay constant, and the formula is related to unstable light rings around a black hole. So, you know, we can now actually determine what is the value of this decay constant, and it can be checked against the light rings around the final black hole. So I am kind of like oversimplifying things a little bit, but at least, you know, this kind of captures the flavor of what is actually happening in space and how these are, you know, related to the things that we want to observe. Another relevant point about light rings is one of the huge news back in 2019 is that we can directly image a black hole for the first time. So this was the picture released back in April. It was announced in 2019, but the observation was made in 2017. So this is the picture over here. It is a picture of a black hole at the center of galaxy M87. So we say that this is a picture of a black hole, and it kind of makes us tempted to say that this dark spot here is the black hole itself. But this is actually not precise. This dark spot is actually just the shadow. So the actual black hole would be roughly a disk that is 2/3 of a size smaller. So this shadow here, the radius of this shadow is approximately equals to the light ring. So this is like almost directly, we can almost directly measure the radius of the light ring using this way also. So yeah, so this picture is kind of a quick depiction that the shadow itself is a dark patch that is larger than the actual black hole. And the way to form the light ring is that if you shine the light at just the correct orientation, it will just the gravity and the motion will balance itself out such that it will make circular motion around the black hole. So these are the light rings that we want to focus on in this talk. So in light ring research, what are the questions that people are working on nowadays? So these are a few sampling of things that we want to find out. The first is the following: do non-compact do compact objects that are not black holes. Okay, so these are not black holes. These are like very dense matter configurations. Can they? Are their gravity still strong enough to form light rings? We have found some examples. So some of them are capable of forming light rings, and I will show you some examples later in this talk as well. But exactly what are the conditions to form the light ring is not very clear yet. So it's not a finished question. And then going back to black holes themselves, black holes do have light rings, but in almost all the black hole solutions that we have, at least the asymptotically flat ones in 4 dimensions, almost all of them seem to have unstable light rings. So what do I mean by the light ring being unstable? So the light ring, as I said, is the light making a circular motion around the black hole. By the way, everyone can see my camera, right? I'm making hand gestures. So the light is going around in a circular motion around the black hole is what we call the light ring. And if the light ring is unstable, what it means is that if we do a small perturbation on the light, there's some disturbance on the path of the light for whatever reason at all. If it's unstable, then a small disturbance will send the light flying away or fall into the black hole. So unstable light rings are a fragile state around the gravitating source. Right? So that is the unstable light rings. And for all the black hole solutions, it seems that almost all of them are unstable. And then, right, on the other hand, if we want to look at stable light rings, so stable light rings are the opposite. So stable light ring means if you disturb a little bit, the light can still continue to more or less go in a circular motion around the object. And we have reasons to believe that stable light rings might cause the space-time itself to be unstable. So it sounds like two opposite things, but the explanation is actually kind of very interesting. Again, I am oversimplifying, but the intuitive picture is that, okay, if we have a stable light ring, a small disturbance doesn't matter, the light will still continue to orbit around the source. Okay, so if the light ring is stable, then other light can also join into the motion. And because the disturbance will still keep everyone together, so more and more light can be collected and you have more and more light going in the circular motion. So that's one thing. On the other hand, right, in electromagnetism or in quantum mechanics, we learned that light carries energy. So like E equals to h bar omega. So that means accumulation of light means that we are accumulating, not question, right? Somebody else. Okay, fine. Accumulation of light means we have accumulating a lot of energy in the light ring. And then also, right, in relativity, with the energy, we know that energy E equals to mc squared. So energy is equivalent to mass. And in general relativity, mass is the source of gravity. So what is happening here is I'm accumulating a lot of light, accumulating a lot of energy, and that means it's equivalent to mass. So this thing starts to form its own mass and start to have its own gravity, and therefore it starts to fluctuate and deform the space-time itself, and that is how it can cause the instability of the space-time. So usually most physicists believe, right, I emphasize, because most believe that stable light rings might imply the space-time to be unstable. Okay, so this is kind of a subject of contention. This is why I say most, because there are some people who argue against this, and there's a lot of subtleties and things which is not the subject of this talk. So I guess for now, for the purposes of this talk, we should keep in mind that what we want to do now is to find light rings around compact objects, whether they are black hole or not, and to check whether they are stable or unstable. Okay, so that is one of the kind of the pressing issues that we want to address here. So moving on to some technical side now, I want to derive the equations of motion to describe the light ring. So I shall start with a general situation, but towards the end, I will narrow down further and further until we have a spherically symmetric configuration in 4 dimensions. But if we start with a general space-time, I can have any d-dimensional space-time with p killing vectors. So the killing vectors are basically the directions of symmetry. If I have p killing vectors, then it is always possible to choose a coordinate system such that I have P coordinate sigma, that these coordinates are aligned along the directions of symmetry. And the remaining directions, I shall call them x1 to xn. So I can choose it in such a way that the space-time metric will be block diagonal. And furthermore, the metric components, GMN and little g, all of them depend on the x only. So none of this depends on the sigma. That will make our calculation much, much easier later. Okay, so this is the general setting of the space-time that we want to consider. And now we want to describe orbits, basically light rings or circular orbits in this space-time. So orbits are curves in the manifold. Therefore, we shall describe them by the parametrized curves. So in general, I will let tau be the parameter of the curve, right? So it depends on the coordinates here. And the curves, the geodesics can explain either light, the motion of light, or massive objects like satellites, spaceship, humans. Those are mass objects with mass. Light are massless objects. So the character of whether an object is massless or massive depends on the tangent vector of the curve. So if the tangent vector is orthogonal to itself, we have now geodesics. These are the motion of light. But if the tangent vector, the inner product with itself is a negative term, which we can normalize to 1, it describes time-like geodesics. Okay, so we'll come back to this equation later, but we want to derive a curve for a particular space-time. So there are many ways to do this. Here, let us start with the Hamiltonian. So from the metric components, we can form the Hamiltonian as the following, where the P and the little p are the momentum. So the big P are the momentum along the sigma directions, and the little p is the momentum along the x directions. So just now I was considering a space-time with p killing vectors, right? So p killing vectors, therefore, because of the Noether's theorem, we will have p constants of motion. This is where the momentum along these directions are constant throughout the motion. So in particular, the first killing vector is a time-like killing vector p0. This will give me conservation of energy, and the remaining ones are the conservation of linear or angular momentum, depending on whether the killing vectors are angular symmetry or translational symmetry. So this equation, which I mentioned earlier, right? If we plug in the expression in terms of momentum, we will arrive at this equation over here. So like I said, the big P are conserved, the little p are not. So this term here is like a p squared with some constants and some coefficients. So this term behaves like a kinetic energy, right? It's like a p squared over 2m kind of thing. And then this here, right? All these p are constant, and by the argument I mentioned earlier, all this depends on x only, x1 to xn. So all these are functions of x. So this is basically like a potential energy function, and this is like a kinetic energy function, which is why we're going to call this expression the effective potential. So this is going to be the main subject that we will manipulate throughout for this work. So this is the effective potential over here, and throughout the entire motion, this expression must evaluate to 0 at all times. So that will give us a constraint on the domain of motion, because right, this is the kinetic energy term, and it can never be a negative number. So because this will always be positive or 0, then particles must move in a domain where the effective potential is negative, right? Because we want the right-hand side to be 0. So given a potential energy function, we can identify what are the regions the particle can move, and what are the regions that are not accessible to a particle, whether they are light or planets or whatever. Okay, so that was the general description of geodesic, but the main subject of this talk are light rings. So light rings are circular orbits. So in a general d-dimensional space-time, let us define circular orbits to be where the x are constant. So this is equivalent to saying that the little p are 0. And if you go through the geodesic equations or the Hamilton equations of motion, you can show that this condition is equal to this one. So the effective potential and the gradient must be 0. This will make the momentum here 0. Okay. So this is for the general d-dimensional space-time. But if we go to the special but very, very common case of 4 dimensions and spherical symmetry, all right, 3 spatial dimensions and 1 of time, I can write down a general metric that takes this form, where f and h are functions of r only, right, because of spherical symmetry. If you go through the Hamiltonian and derive the effective potential, we can show that we can derive that the effective potential can be written in this form, where HR is just some boring functions where depend on how you factorize and rearrange the term here. So the FR is the important thing and the most interesting function that is over here. So with this FR, right, we can derive the conditions for the circular orbit. So the circular orbit condition is where this previous condition is now reduced to f equals to f prime equals to 0. Okay, so these are the circular orbit condition. And also, you can also show that stable orbit requires the second derivative to be negative. And therefore, the unstable circular orbit is the opposite. So here, and the second derivative is positive, which brings us to the point of the inflection point, right? So the inflection point, f double prime equals to 0, here shows us that it is the point where it separates the set of stable orbits from unstable orbits. So this f double prime 0 also will be a point of interest to us later. Okay, so that is our basic description of how to derive circular orbits. So this is a bit of a summary, right? As I mentioned earlier, condition for circular orbit is given by this, or in spherical symmetry, it just simplifies to this equation. And this is where the connection to discriminants come in. So I guess for the mathematicians in the crowd, right, you might recognize this as the condition that defines the discriminant. But this is, of course, only if u or f is an algebraic function, or basically polynomial. So if they are polynomials, then this equation is basically the same as the finding the discriminant. So the problem of finding circular orbits in gravity will be equivalent to the problem of finding discriminants in algebraic geometry, provided, of course, that we are talking about polynomials over here. So this is a bit of a constraint on the problem, but not too much, because in general, most spacetime, the f is some analytic function or numerical solution. But in many examples I will show later, most of them turn out to be polynomials anyway. So that brings us the tantalizing possibility, right? So when over here, when astronomers and physicists, we want to study circular orbits, typically we solve the equation like this. But if we think in the language of discriminants, there are many results in math. Some of them are very elegant and sophisticated and very advanced methods to find discriminants. So this kind of gives us the idea that maybe we can carry over some of the results of discriminant and see whether they can help us to address any problems about light rings or circular orbits around gravitating sources. So which is why we go to the subject of discriminants. So in this part, I'm going to talk about the mathematics of discriminant first. So I should therefore, give a bit of a disclaimer. I am not an expert at all on this subject. Most of this I learned for myself like very recently only, all right? But I will try my best to share with everyone what I have learned so far. Okay. In any case, I'm not worried. In case I make a mistake, Mounir will be hopefully here to point anything out. So yeah, what are discriminants? Discriminants, the natural setting for the study of discriminant will be the complex torus C star n. So the coordinates will be described by z1 to zn. Right? So C star n is just a set of complex numbers with the origin removed. So discriminants are related to polynomials. So eventually we want to describe polynomials, and the way to describe polynomials is we choose a set of lattice points. So So we choose a set of lattice points alpha 1 until alpha n, right? So I'm going to call this set A. It will be the subset of Zn, such that each alpha I here is a lattice vector, which is to say that it is a vector of integer components. So if I write out all the components, I'm going to write it like this: alpha I1, alpha I2, until alpha In. So this will describe the polynomial because this will be the power that will appear in the polynomial later. Okay, so the set A is going to be important for polynomials. And to write down the polynomials themselves, usually we write it in this form, right? It is a sum. Let's say my polynomial has n monomials. So it is a sum of n terms with the coefficients ci, and then the z to the alpha is the shorthand notation for this expression. So we are having n variables here. So z to the alpha means z1 to this power, z2 to this power, until n, right? So this here are the components of my lattice vectors. These are my elements of set A. Therefore, how we choose the set A will decide the structure of this polynomial, and we call this the support set. So these are the set of the exponents that will appear in the polynomial. Another thing that will be also important later are the CI. So if my polynomial consists of n terms, then I have C1 to Cn. So if I arrange this, then this will be an element of Cn, right, in general. And I'm going to call this the coefficient space. This is the physics language of saying things, right? It's not a math definition, but this is going to be important because the C1 to Cn with this physics language is because this will carry information about the energy and angular momentum of the particle, and also maybe the mass of the black hole and things like that. So all this information ultimately will be stored here. So this is, yeah, so that's why I'm calling it the coefficient space. So what's a discriminant and what's the A-discriminant? The definition of it is, well, given a polynomial f, the discriminant we will denote it by dAf, and it is defined to be an irreducible polynomial which vanishes if and only if f has a singular point in C star n. Okay, but this is actually something that is already very familiar to us, and we learned this in high school, right? For example, if we take the quadratic polynomial az squared bz plus c. So the exponents here, this is one variable. The exponents is 2, 1, and 0. So therefore, the support set is just 2, 1, and 0. And we have learned the formula in high school that the discriminant is b squared minus 4ac, right? Where if b squared minus 4ac is positive, this will have 2 real roots. If it's negative, we have 2 complex roots. But what we want to focus on is when this term is equals to 0, we have degenerate roots, or in a more technical language, it has a singular point. And notice that this itself is a polynomial in coefficient space, right? So that is an example of a discriminant. But of course, for the quadratic polynomial, the discriminant is very straightforward. When the degree of the polynomial is higher, or when I have multiple variables, then the expression for the discriminant becomes very complicated, right? So you can look up the Wikipedia of a degree 4 discriminant. It's like a huge mess. It's almost unusable, right? So we can't do it in that way. But luckily, thanks to the Horn and Kapranoff, the results by Horn and Kapranoff, there is actually a very elegant way to find the discriminant of more complicated polynomials. So I'm going to outline this procedure in the next few slides. So to reiterate, right, the polynomial is written in this form, and the Horn-Kapranoff narrows down by taking the lattice components, the alphas, okay, and the procedure is the following. So the first step is, okay, take note of the alpha. Each alpha I are lattice vectors, and over here I'm writing explicitly all the components, such that right now I have an array of numbers. All of them are integers. So the next step of this procedure is to turn this into a matrix. So all these arrays of alpha are all here. So I'm arranging this into a matrix, and I shall add a row of ones up here. And I will still call this matrix by the same symbol A because it essentially contains the same information as previously. So this matrix will determine the structure of the polynomial, right? So in general, I got the n by n plus 1 matrix. So this is the first step. And the next step is to do the Gale transform of the matrix A, which is to say that I solve the linear system A times the vector u equals to 0 and find all the linearly independent solutions. And having all the linearly independent solutions u, I arrange them into a column vector such that this column vector here, I'm going to call this matrix B. So the size of B is n by n minus 1. So here we are assuming that A has the maximal rank. It has a highest rank as possible given its size, right? So the matrix B is the Gale dual of A, and it is the matrix whose columns span the kernel of A. So it will satisfy this equation. So having the support set, I find A, and then I do this, and then I find the matrix B. And this will be a matrix of integer numbers as well. And in the next step, I will look at the rows of the matrices B of the matrix B. Right, so I'm going to let Bj be the jth row of B. And next, I will consider the projective space. So lambda is an element of projective space. And having these two elements, we will define the map, which is called the Horn-Karpanoff map or Horn-Karpanoff parametrization. This is a formula that will give us the discriminant that we are looking for. So the full definition is the map from complex projective space to C star M, where the image of this map is given by this formula. So for each component is the bj's, the jth row of B. So take the jth row of B, take the inner product with the lambda, because lambda also will have m components, and then we raise it to the power of bj1 for the first coordinate. The next coordinate will be raising to the power of bj2 until to the power of bjn. And then also for each component, we take the product over j from 1 to n. So this will describe the discriminant in the sense that the value of this inner product corresponds to the Cj coefficients for the jth row. And the image of this map for all the lambda it will become a surface, a subset in C star M. And we call this the dB, the reduced A discriminant. So the result of this is that, well, the image of this map is an algebraic variety in C star M. So, you know, the complicated formula aside, the picture is pretty straightforward. I have a projective space. The Horn-Karpanoff map is a map from projective space to C star M. And the image of this map is what we are looking for. It is the discriminant. Okay. So this thing here.
Can I ask a question now?
Yep, sure.
So does this mean that every irreducible polynomial has a discriminant?
Yes, right. I think so.
Oh, is it unique?
I'm not sure. I think
Oh, really? So every irreducible polynomial has a discriminant, and maybe it's unique. Okay, that's awesome. Really cool.
Yeah, but it has a discriminant. So
the Gale transform is not unique. I think this responds to your question.
Oh, so there could be more than one discriminant of a polynomial.
The reduced discriminant, it comes from, we compute this using the Gale transform, the matrix B, but the matrix B is not unique.
Okay. Oh,
and this, I think, answer to your question. Thanks.
Okay, thank you.
Okay, yeah. So thanks, Mounir. So this is very clearly his department, but I will try to push on, right? So what we have here, where I left off is we have the discriminant thing over here, and it is an algebraic variety. And as for any algebraic variety, we can find the amoeba by defining the log map. So the log map is like taking a point on the variety, right? The coordinates. We take the absolute value of every component, and then we take the logarithm. So the result of this is what we call the amoeba, and this is one example of the image of an amoeba in two-dimensional R2. So with this picture, it is obvious why we call this the amoeba, right? We have tentacles. This is similar to the biological single-cell organism. So given an algebraic variety, we can define a map to the amoeba. And with the algebraic variety also, right, we can also define another map. So I will connect everything later. So firstly, I got the log map. Secondly, I have the, sorry, I think I spelled this wrongly, the logarithmic Gauss map, where I take a point on V and I map it according to this formula. So this will send this to projective space. Okay, so I have two different maps, and the relation between these two maps is given by Mikhalkin. So given a point on the variety, right? It is a critical point of the log map if and only if I take the same point and do the Gauss map, it will send it to the real part of the projective space. Okay, so essentially what I said just now was described by this picture. Given an algebraic variety, I can define a log map to get the amoeba, but I can also do the Gauss map and send it back to the projective space. So the Mikhalkin's theorem mentions the critical point of the log map. So the image of this map, image of the critical points are the critical values, and we have a special name. It's called the contour, and we'll denote it by C. So it's going to be the subset of the amoeba, which is the image of the critical values of the map only. Okay, so in other words, in pictures, right, I have the log map of the variety and I have the Gauss map of this variety, but there is a subset of points, which these are the critical points, which if I do the log map, it will send to a subset of the amoeba. This will be defined as the contour C. And according to Mikhalkin's theorem, if I take these same points over here and I do the Gauss map, it will send it to the real part of the projective space. Okay, so we are making a big deal about the real part here because ultimately the real part is where the parameters related to light rings and orbits are like energy, angular momentum, things like that. All these are real numbers. Okay, so so this is why we are very interested in this theorem. So the real part will be connected to here, and it will be in this direction. It will be the contour. So how does this relate to the Horn-Krapanov? So the Horn-Krapanov map was a map from projective space down to C star M. And this logarithmic Gauss map is from here back to projective space. And the relation between these two is they are indeed inverses, is the inverse map. So this was proven by Krapanov in 91. The inverse image of the map psi, which I had shown earlier, the inverse of this is actually the logarithmic Gauss map. So when the algebraic variety we are talking about is the discriminant. So yeah, so the psi is the inverse of gamma. So now the picture is almost complete. I have the real projective space, right? If I take the real part, if I do the Horn-Krapanov map, I will obtain this set of points, where if I do the log map, I will get the contour. And by Mikhalkin's theorem, the same point is the one that goes back to the real part of the projective space. So by definition of the Horn-Krapanov, right, we are constructing using the matrix A and the Gale transform B. So the result of this map will be related to the discriminant that we are looking for. Okay, so another thing to talk about is on the contour, right? In the pictures of the contour, you might have noticed that there are sharp corners on the contour. So these are cusps. So the cusp is going to be important to us later. But at the moment in math, right, there is a theorem by Rojas and Rusek, which given a map of given the contour that is a result of this log map of the discriminant, it tells us the number of cusps. So this is going to be the main theorem that will help us answer the question about light rings. So I should take the time to read it out at least. Right? It says that let f be an n variable polynomial consisting of this sum of n plus m plus 1 monomials. So the theorem applies to the case of m equals to 2. And so if m equals to 2, then the image of the discriminant and the contour is going to be in 2 dimensions. can be plotted in 2D. The graph of this will have at most n cusps. Okay, so that is the main result of the Rojas-Rusek's theorem. Okay, so in this example here, I have in particular I have one cusp in this picture over here for the contour. So how did all this math tie into the problem of light rings and circular orbits that I introduced at the beginning of this talk? So let us go back and remind ourselves what we have been discussing. Remember, so firstly, we are focusing on the case of spherically symmetric spacetime, right? So 4 dimensions and everything depends on R only. In this case, circular orbits is defined by this equation I showed earlier, f prime equals to 0. And knowing the language of discriminants and Hahn-Karpranov map, we can find it by doing this dBf, right? The Hahn-Karpranov formula. We can also show that the cusp of the discriminant actually corresponds to the places where the second derivative equals to 0. So remember, second derivative in the orbit, it means that it is the point where it separates the stable and unstable circular orbits. Okay, so the cusp is where, you know, a stable orbit turns into an unstable one, or vice versa. So yeah, so we have this, and then if we are talking about spherically symmetric space-time, everything depends on R, so one variable, n equals to 1. So if we apply Rojas and Rusek's theorem, n equals to 1, that means the contour of the amoeba after the log map will have at most one cusp. Okay, so so this is the image. The theorem was for the contour, but this is just the log map, right? So the picture before doing the log, in all the examples I'll show earlier, will also always have n equals to 1 cusp as well. So that is kind of that is the result that has the implication to the light ring. Even though n equals to 1 sounds very boring out of context, right? But remember, the cusp is the point where it separates the stable and unstable orbit branches. So what we have here is that spherically symmetric spacetime in 4 dimensions can only have 2 branches of circular orbits. Okay, one stable and one unstable. So what is happening here is if I consider all possible circular orbits of this spacetime, right? Let's start from a smallest possible radius. And let's say, like for a random example, let's say this small orbit is stable. So if I increase the radius, means I'm going along the discriminant. So if I'm going along the discriminant, if I increase the radius, then it's going to be like a set of stable orbits of different radius. And then after some special radius, anything after that, it will turn into an unstable orbit, right? So in other words, like I have a stable orbit and then increase the radius. All these are still stable, 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 stable until a critical radius. Anything larger is unstable, all right? So this is 2 branches of circular orbit. And it rules out the possibility, because n equals to 1, only 2 branches, which means that if I want to find a case where I have stable, 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 and then unstable, and then back to stable, no, this thing doesn't happen, right? So that is the consequence by applying the Rojas-Rusek theorem to the geodesic equation. Although there is one caveat, I should say, that in order to use Rojas-Rusek theorem, we must satisfy the conditions. So in the case of n equals to 1, that means my function f here must consist of 4 monomials. So it might be a very constraining condition, but at least for any space-time that satisfy this condition, we know definitely that there is 2 branches of light rings in this case here. Okay, so to see how everything works, right? Let us work out an example. In this example, I'm not talking about light yet. These are orbits of massive particles around a Schwarzschild black hole, right? So this is a very basic example from textbook. So the Schwarzschild black hole, to remind everyone, is described by this spacetime metric where the function f is 1 over 2m over r. So it has an event horizon at 2m. So if you work out the geodesic equation and derive the effective potential, we got this function here. So this is the f, and this is the boring function h, which is not important. But this is indeed a degree 3 polynomial with the coefficients. So let me tidy up the polynomial by writing f as ax3 plus bx. And then if I rescale r into x correctly, I have a and b only. So a can be expressed in terms of the mass, energy, and angular momentum. And same for b, right? So I have this polynomial, it's degree 3. Pretty simple, but we can use the Hahn-Kapranoff map. So, and it is described by this parametric curve. So I can plot this on the a and b axis, and the result is this. Oops. Okay, and as predicted or as proven by Rojas and Rusek's theorem, we do have one cusp over here, right? And then this blue branch is the branch of stable circular orbits, and this red is the unstable ones. So this is plotted in terms of B and A, and it would be much more useful if I translate this back to physical quantities. So to get my energy squared, I recover my energy by taking B minus A over B, and angular momentum per mass is by doing this. So if I transform and plot the curve again, this is what I got, right? The black curve over here corresponds to negative L squared or negative E squared, so it's not relevant to us. But the stable branch is over here, and the unstable branch is over here. So we can show that this is until infinity is 3m, until the cusp, the stable branch, the unstable branch stop at the cusp 6m, and then all these are larger than 6m, 7m, 9, 10 until infinity. So this is the stable branch, this is the unstable branch. The point that separates the two sets is 6m, and this is a well-known point in textbooks, in relativity textbooks. We call it the ISCO, the innermost stable circular orbit, because stable circular orbit exists down to 6m. Anything less than 6m, unstable already. Okay, so now we can prove a further result to actually say whether light rings exist or not. And in fact, one of the questions I mentioned earlier, right? It seems like black holes only have unstable light rings. Am I running short of time? I am, right? So I can go a bit faster. What time are we now? By the way, does anyone have any question? No. Okay, so if not, let's.
Well, you still have 10 minutes. It's okay.
Okay, sure. And Q&A, right? Questions. So I shall talk about this. Let's see how far we go, right? So let me address the question. Black holes seem to have stable light rings, and also, like, you know, remembering the importance earlier, stable and unstable light rings implies the stability of the space-time itself. So if black holes only have unstable light rings, then it is very likely that black hole solutions are stable. So it kind of solidifies the existence of black holes in space. Okay, so because there are also like skeptical arguments that say that black hole solutions are just artifacts of Einstein's equation. And if you work out all the physical properties and factors, the stable black hole will evolve into, the black hole will be unstable, and the space-time will turn into something else, and the black hole no longer exists. So that is why we want to address these kinds of questions here. To answer our question, right, most of our formula works best for spherically symmetric space-time. So we stick to this case here. We still try to be as general as possible under these constraints. Therefore, we consider spherically symmetric asymptotically flat space-time, where the GTT component is written in this form. Let us write it as 1 minus P over Q. So if I want to go to Rojas and Rusek's theorem, P and Q must be polynomials. So this is rational function. And if I want to talk about asymptotically flat space-time, the limit of R going to infinity must be 0. So the degree of Q must be higher than P, at least. Okay. Then for this type of space-time, we can work out the effective potential again, right? We go through the calculation, we get the function f, and our function f is given by this simple form. So eta here is just the ratio of energy to angular momentum squared. Okay, so this is, at the moment, I haven't specified what are the Q and P. Although if I want to use Rojas and Rusek's theorem, this at the end of the day must consist of 4 monomials. So we identified 4 classes of space-time which will satisfy the Rojas and Rusek's theorem. So I think the details doesn't matter, but generally speaking, we do have 4 different rational functions over here, where A and B and C are constants, and the M, N, and L are the integer powers of R. So with this, right, we can finally address the question, do black holes have stable light rings? Well, what characterizes a black hole? The thing that tells us that a black hole exists is the event horizon. And, you know, in concerns of time, I'll just skip a detail. It can be shown that for these 4 classes of space-time, we can derive the effective potential F, and it turns out that the reduced A-discriminant using the Horn-Kapranoff method, upon calculating the results, it turns out that the cusp, right, and Rojas-Rusek said there's one cusp. We have further shown that this one cusp always lie in the parameter space with no horizons. And the implication, you know, this is like the technical details, but the implication is that, yeah, black holes only have unstable light rings. So, I mean, I claim that this is a theorem. The way to prove it is just by brute force calculation. So it's not a very elegant way to show it. In any case, it might be a bit clearer if I work out some examples. So let's take the Hayward spacetime, right, to be slightly more general than the structural black hole. So a Hayward spacetime is a spacetime with no curvature singularity. And depending on the values of M and L, it describes a black hole or a non-black hole object. So it is a black hole if M over L is smaller than this number, and it is a horizonless spacetime if M over L is greater than this number. So it captures both cases. So let's calculate the light rings in this spacetime. So we do the Horn-Kapranoff map, you know, we do our calculation over here, and then we plot our reduced A discriminant in the AB axis, where A is given by eta 2M over L, and B is given by this expression. So because A and B depends on combinations of M and L, right, we can show that above this line here, these are the values of M and L that gives no horizon. So this is not a black hole. But anything here will be corresponds to a black hole. And it turns out that the cusp lie in here as what we calculated. And also, this blue curve is the stable branch. So the stable branch is only within the part with no horizon. And the unstable branch is only, the unstable branch exists here and it persists until it is, even in the case where it is a black hole. So a black hole only has unstable light rings. Okay, so for one final example, we will take the Reissner-Nordström spacetime. It is another generalization of the Schwarzschild solution by including charge. So if the charge in geometrical units, if Q is less than mass, then the solution describes a charged black hole with an event horizon. But if the charge is larger than M, it describes a naked singularity. So this solution has a curvature singularity at the origin, and there will be no horizon covering the singularity if the charge is larger. So there's no horizon, it's just a space-time with singularity. And now let us calculate the light ring around this space-time. So same result as the Hayward space-time. We have one cusp as predicted by Rojas and Rusek's theorem. The blue curve is the stable light ring, the red curve is the unstable light ring. And notice that B, right, B is actually Q squared over 4M. And this point is 0.25, is 1/4. So any points higher than here is the naked singularity. So higher than here is the no horizon space-time, and underneath here is less. So this is where we have the black hole. So the stable light ring only exists for the naked singularity case, but the unstable ones exist for the case of the black hole. So if you're talking about the charged black hole, then it only has the unstable light ring. By the way, as a passing remark, right, I think some of us here know Ong Yan-Ching. He gave a talk in the campus before. He wrote a paper all about this particular right link for this particular point, because this particular point is the extremal black hole, which is also a lot of interesting phenomena here. But yeah, so these are the two examples. And in all the cases, you know, even in the general calculation, as long as the space-time satisfies the conditions for the Rojas and Rusek theorem, every time if you want to find the light ring around the black hole, the light ring is going to be unstable. But if it's a non-black hole object, then according to Rojas and Rusek, it has one cusp, and therefore it has two branches of light ring solutions. Okay, so to be more precise, these are my conclusions. Static, asymptotically flat, spherically symmetric spacetime of the four classes, these four satisfies the theorem's condition. It has two branches. But if we are focusing specifically on black holes, then they will not have stable light rings. Okay, so these are the like the main points that I want to convey in this talk. Although, you know, in this talk seems like we are only scratching the surface. We are focusing on very special cases and using some very specific results, particularly Rojas and Rusek. But there are so many more results of A-discriminants, right? Mounir will talk about more of them next week. So the obvious future work or open questions that we can address is, what else can we use, and what other things we can use from A-discriminant to help us answer questions about light rings, or more generally, the structure of space-time around black holes or compact objects. So yeah, that's all I have for today. Thanks to everyone. Thanks for joining this session. Any questions?
Thank you very much, Yen-Kheng, for this talk. Are there any questions?
Yeah, I have one. Can you give us some idea of how restrictive that Rojas and Rusek condition is? You said that your F must satisfy the hypothesis of Rojas and Rusek, the four monomials thing.
Yeah.
Can you give us an idea of how restrictive the condition is?
Okay, so one restriction is that it is a theorem about polynomials, right? So the geodesic equation must be polynomial. So if the space-time metric is described by functions that are not polynomials, just analytic functions with non-integer powers, then we cannot apply Rojas and Rusek's theorem. So an example would be like the Fisher space-time, for example, or the Louisville black hole and things like that.
Okay.
Yeah.
So this is really quite a special case of polynomials. Polynomials are a very special case of because the function is analytic.
Yeah. So So what I was referring to is where was it? Yeah. So this metric components. It is a special case, but it's not too restrictive because a lot of them also they are still described by polynomials. So at first I thought it's extremely restrictive, but I'm already quite surprised that I can find these two examples already. And there's one more example we added in the final paper that we submitted.
Okay, so sorry. Can I say a few things about this restriction? Maybe next week I will talk about. I mean, this A-discriminant is not only for polynomials. We prove it recently with Rojas. I will talk about this next week for sum of exponential, not only polynomials. So and the result is very new, and I think less than 1 month. So of course, as said Yen-Kheng, there is some restriction, but not too much. You will see next time that the theorem works even for sum of exponential. And exponential, you know, exponential is not algebraic. It's something which is analytic but not algebraic. That's it. And there is for the application of the A-discriminant, we found this is a new project with Yen-Kheng is in quantum mechanics, and in two things, in quantum mechanics and in what we said, the topology of the image of the moment map. And hopefully that we can finish this in 2-3 months or something like that. I hope. I don't know. We'll see. Anyway, we should finish this in maximum 3 or 4 months. So the generalization exists, and other application also exists. Thank you.
Okay. Thank you, Mounir.
Yeah, so to add on, that one is like the results that we are using here, right? Is like we're focusing on the real part. So this is why we're tempted to go to quantum mechanics, because quantum mechanics, you know, we describe them in complex functions, and that is where we can fully use the complex numbers in all its properties.
Yes, let me add another word here. In quantum mechanics, as we use complex number, we want to use, we will use not only the amoeba, we will use other things that we call the co-amoeba.
Yeah.
And the co-amoeba is some set in the real terms. I mean the phases. Okay, thanks.
Yeah.
Okay, are there further questions or comments? Questions by students, maybe? Don't be shy. Okay, if there are no further questions, then let's thank Yen-Kheng again. Oh, actually, have we thanked him? Well, we have no way to applaud here, right? Well, you can use the logos.
Yeah.
Okay. So then I say thank you again, and I invite everybody to Mounir's talk next week. Same time, same well, same place.
Okay.
Right?
Thank you.
Keeps again. Okay. Goodbye.
Same place.
Thank you. Bye-bye.
Okay. Bye, everyone. Thanks. Thank you. Stop recording here.
So, can you stop it? Or do I have to stop it? I think I started it.
Yeah, you can stop and then.
Okay.